After starting this module, you will learn about carbocations. You will also know the methods of generation of carbocation. You shall be able to explain the stability of various types of carbocations and their reactivity.
Dear students, in this module we shall study about the classification of carbocations. Some of this the simple carbocations you are already familiar with, and we shall look at what are non-classical carbocations, which may be a new term to you. And obviously, as the name reflects, they are different from the carbocations which are primary or secondary or tertiary, which are the simple carbocations, and how they are different from them, that we will be studying. Then furthermore, we shall see what are the various methods of generation of carbocations, which will include the ionization. Obviously, when you are having the carbocation which is a positively charged species, then it will require the heterolytic cleavage and it will give rise to the corresponding carbocation via either ionization, or it can be ionization after an initial reaction, or it can be generated by the attack of pi system on electrophiles, or they can be generated as non-classical carbocations. Then we shall also see and understand the structure of carbocations and how that will be affecting on the stability of carbocations. And the stability of carbocations, when we try to understand, we will see the role of inductive effect, hyperconjugative effect and the resonance effect, and try to see the order of stability of the various carbocations. Then we shall also focus our study on the reactivity of carbocations in this module. Let us now summarize what we have learnt in this module. Dear students, in this module you have learnt about that carbocations are reactive intermediates and they are electron deficient species with sextet of electrons, that is, they have 6 electrons in their electronic configuration of the carbon bearing the positive charge. And we have seen that the stable carbocations can be generated in superacids. We have also understood with the help of the inductive effect, hyperconjugative effect and resonance that how, if the positive charge can be decreased on the carbon bearing the positive charge, then that carbocation will be stabilized. And we have seen that the electron donating groups, which will impart either the plus I or they will contribute via resonance, will be making them more stable. On the other hand, if there are electron withdrawing groups attached to the carbocation, then that will be comparatively less stable. We have also seen that how the carbocations can undergo various types of reactions, such as they can capture nucleophile, they can undergo elimination and they can undergo rearrangement. So, this will give you the overall idea that further organic chemistry, when you are dealing with the carbocations as the intermediates, then wherever the carbocations are formed, if there are more than one possible intermediate carbocations possible, then the one which is more stable will be the favored route. So, all this will be helping you in the further organic chemistry study.
You are already familiar with what carbocations are. They are the species with trivalent positively charged carbon. They are also called as carbenium ions. They are formed via heterolytic cleavage in an organic molecule where carbon donates the shared pair of electrons to the leaving group, which results in the development of a positive charge on the carbon atom. Carbocations are generally unstable because they do not have 8 electrons to satisfy the octet rule. The carbocations have been categorized as classical and non-classical carbocations. Classical carbocations include methyl, primary, secondary and tertiary carbocations. You are already familiar with the methyl carbocation. Primary carbocations are those in which the carbon bearing the positive charge is attached to one carbon of an alkyl or aryl group. In secondary carbocations, the carbon bearing the positive charge is attached to two alkyl or aryl groups. In a tertiary carbocation, the carbon bearing the positive charge is attached to three alkyl or aryl groups. Let us now understand what are non-classical carbocations. In simple words, non-classical means non-conventional or unusual or different from classical. These are the carbocations in which, rather than a particular carbon having the positive charge, the positive charge is delocalized over three carbon atoms as a bridged cation involving 3-center 2-electron bonding. Notice in this case as shown here. These three carbon atoms are involved in 3-center 2-electron bonds. Let us consider another example of a non-classical carbocation, the 2-norboronyl cation as shown here. Notice that the positive charge is delocalized over the three carbon atoms labeled as 1, 2 and 6. This is a resonance hybrid 3 canonical forms where positive charge is localized at each of these carbon atoms. Let us now study what are the methods available to generate a stable or unstable carbocation. The most common ways are ionization after initial reaction, attack of pi system on electrophiles. Let us try to know more about them with examples. During direct ionization, a leaving group attached to a carbon atom leaves with its pair of electrons, resulting in the generation of a carbocation. For example, as shown here, during solvolysis, an alkyl halide ionizes to the intermediate carbocation and the corresponding anion. Though the simple alkyl cations are not stable in ordinary strong acid solutions, example sulfuric acid, but many of them could be stored in stable solutions in mixtures of fluorosulfuric acid and antimony pentafluoride. Mixtures of antimony pentafluoride, usually dissolved in sulfur dioxide, or sulfuryl fluoride chloride, are the strongest acidic solutions known as superacids. For example, the addition of alkyl fluorides to antimony pentafluoride results into the formation of a stable carbocation. Superacid reacts with alkanes as well. For example, at 140 degrees Celsius or 284 degrees Fahrenheit, it converts methane into tertiary butyl carbocation, a reaction that begins with the protonation of methane as shown here. Sometimes the functional groups present in an organic compound first undergo an initial reaction which converts the functional group into a good leaving group, which can then ionize into a carbocation after removal of the leaving group. For example, as shown here, the protonation of an alcohol gives an oxonium ion which ionizes to a carbocation with the loss of water molecule. When an electrophile adds to one of the atoms of a pi system, the adjacent atom acquires a positive charge. In case the positive atom is a carbon, a carbocation is formed. For example, attack of an alkene on an electrophile like proton results in development of positive charge on the adjacent carbon atom to give a carbocation intermediate. Let us now learn how non-classical carbocations can be generated. Let us consider an example to understand this. During the acetylysis of anti-7-norbornyl tosylate, the tosyl group is removed with strong anchimeric or neighboring group assistance by the double bond. It results in the formation of a non-classical carbocation as the intermediate. It is important to note that the stereochemical configuration is retained in such a case. Let us go through the various features of a carbocation. The carbon bearing positive charge of a carbocation is sp2 hybridized, has a vacant unhybridized p orbital. It has a planar structure with bond angles separated by 120 degrees. The positively charged carbon is trivalent. The positive carbon has sextet of electrons. Thus, it is electron deficient. Stability of a carbocation is governed by factors such as inductive effect, hyperconjugation, or resonance effect. The stability of a carbocation is decided by the nature of the groups attached to it. The groups attached to the carbon having positive charge may be electron donating or electron withdrawing. If the groups attached to a positively charged carbon are electron releasing, they will decrease the intensity of the positive charge on carbon, hence making it more stable. If the groups attached are electron withdrawing, they will increase the intensity of positive charge, thus destabilizing it. The more are the number of such groups, higher are the corresponding effects. You are already aware with the order of stability of alkyl carbocations, that is, third degree being most stable, followed by second degree and then first degree, and then methyl carbocation. This order of their relative stability can be explained by both inductive effect and hyperconjugative effects. The plus I effect of the alkyl group pushes two electrons towards the electron deficient carbon, making it more stable. In tertiary, there are three inductive alkyl groups, in secondary, two, in primary, one, and in methyl, none. In terms of hyperconjugation, more are the number of hyperconjugative structures via the involvement of alpha CH sigma bonds, more is the delocalization of positive charge and hence higher stability. For the carbocations shown here, there are 9 hyperconjugative structures in case of tertiary, 6 in case of secondary, 3 in case of primary, and none in case of methyl. Allyl and benzyl carbocations are stable due to resonance. Let us extend this understanding for the comparison of carbocations which are joined to heteroatoms or groups having more than one effect, which may be sometimes opposing as well. Of the three carbocations, let us compare the differentiating groups amongst them, which are CH3, OCH3 and CHO respectively. Let us write what effect they are exerting on the carbocation center. In A, the group is CH3, which is exerting both plus I and plus H effect, of which plus H is dominant effect. In B, the group OCH3 is exerting both minus I and plus M effect, of which plus M is dominating. In C, the group CHO is exerting minus I effect only. Note that it is not exerting minus M effect as it is joined to a carbocation and not conjugated system. It cannot withdraw electrons by minus M as there are no electrons further. Clearly, the most stable is B because of plus M effect, followed by A because of plus H effect, and C is least stable because of minus I effect. Let us consider another example. Before analyzing such a case, one must always keep in mind that whenever two groups in a phenyl ring are at ortho or para positions, they exert all effects, that is M, H and I, on each other. At meta position, they exert only inductive effect on each other and not mesomeric or hyperconjugative, as they are not in conjugated positions. The differentiating groups have been highlighted and the effects they are exerting on the carbocation center are shown. It is clear why the order of stability is B greater than C greater than A greater than E, which is greater than D. Let us now understand what happens to a carbocation during a chemical reaction. As carbocations are most often short-lived, transient species, they react further without being isolated. Thus, the fate of carbocation depends on its reactivity. Once a carbocation is formed, it may react with a nucleophile to give SN1 product. The carbocation may lose a proton to give an E1 product. It may rearrange to another carbocation. It can add to a pi bond, or it may react with the leaving group to return to the starting material. Let us recall some examples of reactions involving carbocation intermediates that you are already familiar with. One such reaction is the addition of hydrogen bromide to propene. This product form is according to Markovnikov rule. It proceeds with the formation of a more stable second-degree carbocation which is further attacked by a bromide ion which acts as a nucleophile. The pinacol-pinacolone rearrangement is another such reaction which involves carbocation intermediate. In this reaction, the tetra-substituted 1,2-dihydroxy compounds known as pinacols, when attacked by acids, undergo dehydration to form carbocation as the intermediate. It further undergoes rearrangement via an alkyl shift followed by deprotonation to form a ketone known as pinacolone. Let us now summarize what we have learnt in this module. We studied that carbocations are reactive intermediates, Carbocations are electron-deficient species with a sextet of electrons. Stable carbocations can be generated in superacids. Factors such as inductive effect, hyperconjugation, and resonance affect the stability of a carbocation. Carbocation can undergo various types of reactions such as capturing nucleophile, elimination, and rearrangement.